All right, so we're going to finish up this week with section 5.4, part 1, which is on logarithmic functions. The idea of a logarithmic function is it undoes an exponential, or it's the inverse of an exponential. So where you would use a logarithm, if I gave you this equation, very simple equation, 2 to what power is 10? Okay, the problem with it is that you have a variable in the exponent. So you can't use addition, subtraction, multiplication, division from algebra 1. If you had this, you could. 2 times y is 10. That's easy enough. But we gotta use a logarithm. Anytime you have a variable in the exponent, that's what logarithms are used for. Okay, so I want you to remember something. I don't know if you studied it in algebra 2, but there's also something called a horizontal line test. Okay, a vertical line test tells you if something is a function. The horizontal line test tells you if the inverse of what you're looking at is a function. Okay, so if you have a graph, you have a relation, and it passes the horizontal line test, which means a horizontal line never hits it more than once, then the inverse of what you're looking at is a function. So for example, a parabola. A parabola fails the horizontal line test. A horizontal line hits it twice. So what that means is if you were to graph the inverse of a parabola, which is, do it like this. Here's your parabola. The inverse of a parabola would look something like this. Since a parabola fails the horizontal line test, its inverse is going to fail the vertical line test. So in other words, the inverse of a parabola, when you draw it, is not a function. Okay, now I want to think about exponentials. Okay, growth or decay, doesn't matter which one. Do exponential functions pass the horizontal line test?
Well, yes.
If you draw a horizontal line, would it ever hit an exponential curve more than once? No. No? Okay, exponential curve could look something like that. Okay, no matter where you put a horizontal line, it's only going to hit it one time. So, since an exponential function passes the horizontal line test, and I said earlier that a logarithm is the inverse of an exponential, that means that logarithms are functions. Okay, since exponentials and logs are inverses of each other, exponentials pass the horizontal line test, the inverse of an exponential will pass the vertical line test. And we call that inverse a logarithm. Okay, so logarithms are functions.
No, by inverse you don't mean a reflection.
Well, yes, there is a reflection. To generate an inverse, basically if you draw in the line y equals x, and you reflect something over that line, that is its inverse. Okay, so here's an example of, in blue, we have an exponential. In red, we have a logarithmic function. And then in black, I drew in the line y equals x. The red line should continue downward like that. So if you take what's on the blue part and you flip it over that black line, you'll get the red part. And those are reflections, which means they're inverses. In fact, you can do that with any function. If you've got a function like y equals 3x, and you want to know, actually make it like that, y equals 3x plus 2. And you want to know what the inverse of that function is, if that's the original, just take all your x's and y's and switch them. That function that I just wrote, that's the inverse of the original. It's basically just switching the x's and the y's, or reflecting over the line y equals x. Now, if you wanted to see that on a calculator, of course, you'd have to solve this for y by bringing the 2 to the other side, and dividing everything by 3. But that, and those are inverses. So if you have a minute later, try graphing them, and you'll see that they are reflections of each other over the line y equals x. Okay, any questions on that? All right, so that's what a logarithm looks like when we write it. And just to be clear about kind of where stuff is positioned, let's say this was your lined paper. And you had y equals, you have log. The a would be below the line, and the x would be right on it. And the way you pronounce that is y equals, or y is, the log base a of x. A and x are usually numbers. Like you could have log base 2 of 5. And we could type something like that into the calculator. So y equals log base a of x. So there are no exponents in this expression. A is a subscript. Okay, it's below it. An exponent would be something like this. Now we have an exponent of 2. Okay, but written like that, there's no exponents there. So some people think the x is an exponent on a. Nope. The x is right on the line. A is actually below. It's a base on your logarithm. The x is the argument to the log function. Okay, it's what you're plugging into log. So on our calculator, we might want to say find the log of 5. Okay, so when you press log and you press 5, 5 is the argument to the log function. It's the thing being plugged into log. And we get an answer. Just like if I asked you for square root of 5. There you go. In that case, 5 is the argument to the square root function. Okay, it's the thing you're plugging into it. Okay, if the base is 10 on your logarithm, okay, that one has a special name. That's called your common log function. And when you press the log button on your calculator, that's the base it assumes you want to use. Okay, so when you press that button, you're taking a log with a base of 10. How do we know that? Well, if you don't see a base written when we're using logarithms, we always assume that it's the common log, or base 10. Okay, so if your base is 10, you don't have to write it. If you want to do something other than base 10, you do. You have to write what base you want to use. Okay, so base 10 is your common log. Does anybody remember what other number we talked about yesterday? I said this number is going to be used as a base on a logarithm, and it's the other one that has a special name. What was the name of that letter? It was a letter. Yeah.
Oh, I don't know the name.
Nick?
It was E.
E.
Natural something, right?
Yeah. So that's our other special logarithm. Okay, if you have a base of E, log base E, that's called the natural log. Okay, and we have a button for that too on the calculator. But the button doesn't look like what I have written there. Okay, in fact, what I have written there, most textbooks and people never really write that way. Okay, we use an abbreviation because log with a base E is used a lot. Okay, and the abbreviation for it is a lowercase l, lowercase n. ln. So it's just a short way of writing log base E. So anytime you see a log base E, you can change that to the abbreviation ln. Okay, let me show you on the calculator where that is. Okay, it's actually right below log, ln. Okay, so let's say I type in ln of 5, I get 1.6. Now, this calculator will actually allow me to type logs in with different bases, other than 10 and e. Because up until now, I've only showed you these two buttons. So if I said to you to do log base 7, well, right now, we don't know how to type that in. You don't need a fancy calculator like this to do it, but let me show you. If I do log base e of 5, what should I get? Yeah, I get that 1.609. Okay, so log base e is the same as ln. All right. And if you don't have a calculator that allows you to change the base, eventually I'm going to show you how to do it on any calculator, even just a scientific one. Okay, but I just want to show you that those two are the same thing. Any questions on that abbreviation? Okay, it does seem a little bit weird that the two letters kind of seem backwards sometimes because it's natural log, and they put ln instead of nl. But that's just the abbreviation we use. All right, let's look at a picture of a log function, okay, and see what it looks like. If you know that it's a reflection of an exponential, you can already kind of think about what it's going to look like a little bit. But let's actually sketch it. Okay, so I'm going to sketch log of x. What base is my calculator assuming there? Yeah,
10.
yeah, it's assuming 10. Okay, and where does it look like on this graph the smallest x value you can use is? What number?
0.
0. Okay, let's try the table and see what we get. So we do get an error at 0. Okay, so we can't take the log of 0, but you can get as close to it as you want. Okay, so your domain is everything from 0, not including it, up to, and I mean you can go as high as you want. Notice though, when I plugged in, what's that? Almost 10 million? Look at what y was. When x is almost 10 million, y is only 7. About 7. Okay, so what does that tell you about how quickly this function grows? What is it? Very slowly. Okay, it doesn't have a horizontal asymptote. Okay, the bigger you go, the bigger y will get. But y does not grow very quickly. But the range does go from negative infinity to positive infinity. Right? You could see it went all the way down to negative 10. The graph, it's not going to look right on your screen, but that blue line should drop all the way down. Okay. So that's where your domain and range come from. All right, next thing we're going to look at is how we can change something from logarithmic form to exponential form. Okay, so here's our formula to do that. If you have y equals log base a of x, and you want to change this into something that doesn't have a log, okay, well, I always start with the a. A was the base on my logarithm. It becomes the base when I write it as an exponential. Okay, the next thing I look at is the thing that was by itself here, the y, okay, on the side with the logarithm. Logarithms are always used to calculate exponents. So I always remember logarithm equals an exponent. So when I rewrite this as an exponential, since logarithm equals the exponent, y becomes an exponent. So now I've got my base, I've got my exponent. There's only 3 things and there's only 3 spots in this equation. So once you get 2 of them, then the x just goes by itself on the other side. So if you wanted to solve this equation I gave you earlier, the way you'd do it, you'd take and put it in log form. In this case, this represents that. 2 is your base, and your exponent is right there. So I use different letters, but it's the same idea. Okay. And then you'd have to translate where each of those letters go on the left-hand side. So let's try that. Let's take something that's a logarithmic expression, and we're going to change it to something that doesn't have the word log. Okay, so start with your base. Okay, what is your base here? Oh, Michael? 3. Yep. 3 is my base. Okay, and earlier I said a logarithm always equals what kind of number? The logarithm always equals, it's used to solve for what? That's Silvio? Think about, he said here, so logarithms are always used to solve for, well, what does that represent though?
Oh,
Exponents. Remember, logarithm always equals your exponent. Okay, so y is the exponent. Okay, what's the only letter that we haven't used? Sam?
X
Yep, and where's the only place for it to go?
on the other side of the equal sign.
On the other side. So we just change it from a log expression to an exponential. We can't solve it because we don't know x or y. We need one of them. If we knew y was 2, then we could do it out. Okay, but that's all we had to do. Okay, let's try this one. Okay, how about Tahina? What's my base here? Yep, base is 5. And my exponent, Brian?
Y.
Yep, logarithm always equals your exponent. And we haven't used the argument that goes by itself on the other side. Okay, so that's changing log form to exponential. Let's try it the other way. If I'm going to change this to log form, what's the first thing I should probably write down? If it's going to be in logarithmic form. Yeah? Yeah, I need the word log. We're changing it to a logarithm. Okay, Nick, what's my base this time?
1.2.
Yep, the base on my exponential becomes the base on my log. Okay, and logarithms always equal what kind of number? Lasan? Logarithms always equal an exponent. What's my exponent here? 3? Okay, so now the only thing I have left is, Shannon, what letter? M, and that's the argument to the log function. All right, and let's try this one. E to the B equals 9. Okay, Julia, what's first thing I should write down here since I'm changing it to a log expression?
Log.
Yep, I'm going to put the word log. Okay, Orlando, what is my base?
E.
E? Yep, we're going to come back to that in a second. So we have log base E. Okay, and my logarithm always equals what, Sam?
An exponent.
Always equals an exponent. What was my exponent here?
B.
B. And the only thing I have left is the 9, and that is the, what's the name of the 9? That's the argument to the log function. Okay, now if you didn't know anything else about E, I would say this is okay. But I explained something earlier about this. We looked at it on the calculator. How can you rewrite that a little bit more simply? Josh?
ln times 9 equals 8.
Careful. It is ln, but not times. There's no times in this whole thing. Any more than if you write this, there's a times in it. There's no times in it. So just change one word and then it's going to be perfect.
ln of 9 equals b?
Yeah, ln of 9. So 9 is being plugged into the ln function. Okay, and if you wanted the answer to that, you could just type in on your calculator ln of 9. And it's about 2.2. Okay, so that's changing from exponential to log. Yeah?
Would we do it the same way if the log wasn't the common log function?
Yeah, like in this one, we didn't have a common log. We had a base of 1.2. Yep. So whatever your base is on the exponential, that's the base on the log. If it's 10, you could get away with not writing it though. Because we said earlier, if you don't write it, we assume it's a 10.
So like if it was 10 to the 4th, you could just write log equals 4?
Yeah, you could just put log, you don't need the base, and then the 4 would go on the other side, and then whatever your variable was.
Okay. And then, was there, you could use the, there's no like ln is for natural log?
ln is always for natural log.
There's no like shorthand for common log?
Well, the shorthand is just leaving the base off.
Okay.
Yeah, just writing the word log. Yeah. Okay, I want to show that log base 2 of 8 equals 3. Okay, what's the only thing we know how to do right now that if you have an expression in log form, what can we do with it? It's only one thing we know. Yeah?
Change to exponential.
Just change it to exponential and see what happens. Right? So Andrew, what's my base here?
Your base is 2.
Yep, base is 2. Logarithm always equals, what kind of number, Carly?
Exponent?
Yep, always equals the exponent. So in this case, 3 is the exponent, and 8 goes on the other side. Well, once we do that, 2 cubed is 8. Makes it pretty obvious why log base 2 of 8 comes out to 3, looking at it in exponential form. Okay, any questions on that? Okay, let's try this. So it says to find x. And I want to know it's log base 5 of 1 over 25. Now, for up till now, I have to pick numbers that are powers of the base. Because I haven't showed you how to plug in bases other than 10 or e on a calculator. What can I do with this expression? It's a logarithmic equation. I can change it to what? Yeah?
An exponent?
Yeah, exponential. What would that be as an exponential equation?
It would be 5 to the x equals 1 out of 25.
Yes. At this point, we have to just figure out how to solve that, kind of by inspecting it, just by looking at it. So if you're not sure how to solve it, I would say start with this. Figure out 5 to what power is 25. And then figure out what kind of number do you need as an exponent if you want your answer to flip. And that will tell you the answer for x. Yeah?
Your x would end up being -2 because you flip your negative exponents.
Right. Okay, so 5 squared would give you 25. But if you want to flip that, a negative exponent causes it to go into the denominator. And that's exactly what that would be. So 5 to the -2 is 1 over 5 squared, or 1 over 25. So anytime you see a fraction, okay, just use a negative exponent, and you can get that in the denominator. Okay, now the last problem was in log form and we change it to exponential, we're going to do the same thing again. It's in log form, let's try changing it to exponential. Okay, Brandon, what's my base here? 5. Yep. And Justin, my exponent? So logarithm always equals the, so, well, one sec. So your logarithm always equals what kind of number? Yeah, logarithm always equals the exponent, so yes, in this case 1.5. And then what about the x? Where is that going to go? Sam?
On the other side. Yep,
on the other side. Now we just have to type that in. 5 to the 1.5. So the answer is about 11.18. Okay, any question on that? Okay, so since we don't have that many things we can do yet with logarithms, we always change it to either exponential form or to log form. That's all we know how to do right now. All right, so here's some special properties of logs. We're going to look at four special properties. Okay, the first property is if you have a raised to the log base a of x, what ends up happening is this whole part right here kind of cancels out. And it's because you're taking a base and you're raising it to a logarithm with the same base. So if these bases match, the answer that it simplifies to is whatever is pretty much right there. They cancel out. Okay, rule 2, it's similar. If you take a log with a base of a, so if these match, your base and your argument has an exponent on it, the exponent is your answer. It's kind of like that first part just cancels out. Right, let's look at the second one and see why it's true. Is rule 2 an equation in log form or exponential form? What form is that? Yeah?
It's in log form, but it has an exponent.
Yeah, it is in log form. Okay. Here's your base. Here's your argument. Here's the thing that's on the other side. Okay. Let's see why that's true. Okay, what did I just say the base was on the log here? Nick? Yep, our base is A. Right there. That's your base. And logarithms always equal what kind of number, Brian? Exponent. So what would be my exponent here?
X.
Yep. So logarithm equals the exponent, and there's your exponent. The only thing we haven't used is the argument. That goes by itself on the other side. Okay, well, writing that in exponential form, it makes it pretty obvious why that's true. That's the reflexive property. Something equals itself. A to the x equals a to the x. We could also do that with rule 1 and prove why that's true very easily. Okay, here's another one. Log base a of a equals 1. So if your base and your argument match, you always get 1. Let's write that in exponential form and see what happens. Julia, what's the base on the logarithm there? Yep. Your base is a. How about, Michael, what's my exponent?
1.
1. Yep. And the only thing I haven't used is the argument. And that goes on the other side by itself. So all rule 3 is saying, if you raise anything to the first power, you get the same thing back. You already knew that rule, except you never saw it probably written as a log. You've seen it written as an exponential. Anything to the first power equals itself. But that's all Rule 3 is. And Rule 4, you've also already seen this rule. Rule 4 says if you take anything, raise it to the 0 power, what do you always get? 1. Anything to the 0 power is 1. Again, another very basic idea, just written as a logarithm rather than as an exponential. Okay, so on the right, these are kind of the reasons why the rules on the left are true. That's all those are. All right, so what we'll have is some problems that look similar to one of those 4 rules. We just have to kind of match up which rule it is and then look at the rule and see what it simplifies to. So we have an exponential expression where we have a log and the base matches the base of the exponential. Which rule is that similar to? 1, 2, 3, or 4? Yeah.
1.
Yeah, that's rule 1. So what are we going to get for x using rule 1? Okay?
Pi.
Pi. You're going to get pi. X equals pi. Let's look at B. We have a logarithm where the base and the argument match, and there's an exponent on the argument. Okay, which rule does that look similar to? Taking it? Which one? Rule 2, yeah. So what do you get for an answer here? Yep, you get -4. How about this one? Little tricky. Ln of e to the kt. Anybody see which rule that looks similar to? To think a little bit about what ln means. Josh?
2.
Rule 2? Yeah, that's rule 2. Can you explain why?
Because the ln of e is log base e.
Right. This whole thing right here can be written as log base e if you write it the long way. And now the rest of it is e to the kt. This is exactly rule 2. So what would be my answer there, Josh? K times t, yeah, whatever that is. Yep. So there's not really much in terms of arithmetic here. You're just looking for a pattern. That's it. All right, so the last thing we'll look at is how we can take logarithms and combine them or separate them. It's kind of like the combining like terms of logarithms. And here's our first rule. There'll be 3. If you have the logarithm of a product, you can split that apart into 2 separate logs. Each log has the same base as the original. That doesn't change. And when you have a product, it splits as addition. So here's an example with numbers. If you took log of 4 times 5, that would be the same as log base a of 4 plus log base a of 5.
So if you have log a of 20, could you factor 20 into 4 times 5? Not do that.
Yeah, and if you write it as addition, it's equivalent to log 20. So what you can do is this. You can take the log of 20, and that's going to be exactly the same as the log of 4 plus the log of 5. I'm doing it with a base of 10, only because that's easy for me to type in. Anybody see a different way I could add 2 logs together and get the same answer besides 4 and 5? Yeah?
Log times 2 or log of 2 squared plus log of 5?
Okay, that would work since 2 squared is the same as 4. How about different numbers than 4 and 5? Yep.
Log of 2 and log of 10.
Yes. Because any two numbers that multiply together to give you 20, when you add them as logs, are going to give you the same answer. So you could also do log of 40 and log of a half. There's infinitely many ways to write the log of 20. Okay, so that's our rule, and that only works if you have multiplication. What do you think if you have division? What do you think is going to be the rule for dividing? Yeah.
Would it be subtracting something?
Yeah, you subtract. And the order you subtract is important. It's the log of the top minus the log of the bottom. Notice the base stays the same as it was originally. And I'm not going to type it in, but here's an example with numbers. Log of 4/5 would be log 4 minus log 5. Keep the base the same. Okay, and then our last rule, rule 3. Rule 3 is kind of like, it's what's similar to rule 1. It says that if you have an argument, or I'm sorry, an exponent on your argument, you can take and put it in front. So log base A of m to the r becomes log r times log base A to the m.
So there's an invisible multiplication.
Yep, there is multiplication here now. Yep. So you can take exponents on arguments and put them in front. Okay? Like that. Okay, let's look at a second and see why that works. It's actually a very, very simple reason why it works, as long as you understand rule 1. Okay, so let's look at log base 10 of 3 to the 5th. What does 3 to the 5th power mean? If you had to write that out in a way that didn't involve an exponent, because you're trying to explain it to somebody that doesn't understand an exponent. What does 3 to the 5th mean?
3 multiply by itself 5 times?
Yeah, it means 3 times 3 times 3 times 3 times 3. Now if we look back at rule 1, I only wrote it for a product of 2 things, but it could be a product of as many things as you want. So when we have a product, it splits as a what? Yeah?
Addition?
Addition. So we could split this into 5 additions. We'd have log, and I'm not going to keep writing base 10 because I don't need it. It would be log 3 plus another log 3. Okay, I'm going to have that 5 times. Plus log 3, there's my third one, fourth one, and my 5th one. How many of the log 3s do we have?
5?
Yeah, we have 5 of the log 3s. That's why you can take an exponent and put it in front. Okay, the other thing to remember, we actually just went over this a couple days ago. If you have a square root, you can write that as something to the 1/2 power. The reason why we might want to do that is because if we have something as an exponent and it's a log, we can put that number in front. So we'll try a few examples taking logarithms and splitting them apart, and then we'll try combining them back together.
Why was that square root of x equals x to the half? Why is that? What are we going to use that for again?
You'll see when we're going to do one with a square root in a second, you'll see. Okay, so we have log base 4 of 3x. When we split this apart, will it be a sum or a difference? Oh, a sum? Yep, it's going to be a sum. So we're going to have log. Okay, Okay, Taylor, what's going to be the base on each of those logs?
4.
Yep, it doesn't change from what it was originally. Okay, and Shannon, what will be the argument to my first log?
3.
Well, what would that leave for the second log then? Nothing. Yeah, just 3. So think of it as 3 times x, just like we had m times n earlier. So it's 3. And the argument to my second log, Brian?
X.
X. That's it. That's how you take a logarithm and split it apart. Now, the first part of this, we could actually type into a calculator if we knew how. The second part, well, if I had a number on the other side, now I could solve this for x. Since I don't have a number, it's not an equation, it's just an expression. Let's try this one. So Andrew, is that going to split as a sum or a difference?
It is going to split as a sum.
Yeah, it is a sum. It's something times something. Okay, there's an exponent here, which means we have to deal with it. But overall, it's just something times something. So log. What's going to be my base, Justin, on each log? 2. 2. Okay, Carly, the argument to my first log? 5. And now the argument to the second log, it's a 2-step process. We can do it all at once, or we can write it twice. Do you think they could do this part all at once? Think about what the argument would be, and then think about what's going to happen to the exponent based on the last rule I just showed you. Yeah, Brandon?
Maybe 3 log for argument.
Yes. So you could start by putting log of r cubed, but then you have to remember the cube goes in front. So on a test, I would write something like express all exponents as factors. Don't leave them as exponents. Okay. Let's look at this one. Sam, is that going to split as a sum or difference?
The difference.
Yep, that's a difference because we're doing division. The base on each log is a 9. First argument is x. Second argument is 2. Any questions on how that's split? Yes?
So wait, is the operation that you're multiplying the log 9 times x over 2, or is it one whole?
No, there's no multiplication in that whole thing. Yeah.
For the logarithms.
So go ahead, ask me one more time.
So right, when you have the x over 2 in parentheses and through all the rest of these expressions,
Yep.
is it the log of 9 times x over 2?
Log base 9 of.
Okay.
It's like saying square root of 3. We wouldn't pronounce this as square root times 3. Square root times 3 would mean this, which doesn't make sense. You've got to have something to plug into a function. So in this case, x divided by 2 is being plugged into the log function. Okay, another way to think about it, the way I explain functions in Algebra 1, I say you've got your function box here. Okay, you have an input. X divided by 2 is being plugged into the function box. And then you're going to get an answer out. We don't know what the answer is because x is a variable. When I do it in Algebra 1, I usually do it with numbers. But that's how you can think of it. This is getting plugged into the function box, and then something comes out of it. And let's look at this one. Natural log of y cubed divided by 8. We can do it exactly the same way. All these formulas apply to any base you want. Okay? Even base e, which is what this example is. Anyone think they could tell me the whole answer there? Yeah?
So 3 log base e y
Okay, so I'm going to use our abbreviation since it's shorter, so 3ln y. Yep.
minus log base E or ln 8.
Yep. Anytime you can use the ln, we will, because it's shorter. But that's perfect. 3 ln y minus ln 8. Let's do one with a square root. Okay, so this is the hardest one you could have. It's kind of got a little bit of everything in it, but you just do it one step at a time. First thing I look at is I see a fraction. So first, let me just take care of that. So I'm going to split it as log base a of the top minus log base a of the bottom. Forget what's actually in the top and the bottom. Just think of it as log of the top minus log of the bottom. Let's write it this way. All of that gets plugged into the log function. Okay, now looking at the first part, what did we say earlier about a square root? Instead of writing something as a square root, what power can you use? What's that? You can use a 1/2 power. So I can have log base a x squared plus 1 to the 1/2. Now, what can I do with the 1/2? Because it's a exponent on an argument in a log. Where can I move it to? Right? I can put it in front. So I'm going to do that all in the same step. That's why we write things with numerical exponents rather than radical symbols. So we can put the 1/2 in front. This first part is done. Okay, there's nothing else that needs to be done to it. You can't split a sum. You can split a product and you can split a quotient, but not a sum or a difference. Okay, now we're going to work on splitting the second part. What is the second part split as? Is this a sum or a difference when you split it? Yeah. It's a sum, because we have multiplication. X cubed times x plus 1 to the 4th. So the first part would be log base a of x cubed, but what can I do with the cube? Yep, we'll put it in front. Okay. Plus, and leave a little space. Log base a of x plus 1. All of that is to the 4th power, but what can we do with the 4? Put it in front. And the reason I left those brackets there is because you're subtracting this entire thing. So if you were to do it out, it's a distributive property. Okay, we're not going to do it out. We're just going to leave it like that. Okay, so any question on the splitting? Splitting, I think, is harder because you're taking something that's already condensed and now you're making it bigger. Okay, when we reverse it, it starts to get simpler at each step. You're taking something that's not simplified, and now you're making it simplified. Okay, so to reverse it, all you have to do is think of everything you would have done to get this as the final answer, and reverse all those steps. Okay, so you have a 4 in front. Where would that 4 go back to? If we're reversing everything we just did. Josh? Yeah, it's going to go back up as the exponent. And now we have to look, we have a sum. So when we combine a sum together, is that a product or is that division? Yeah, go ahead. Yep, that's a product. What's going to be my first factor, Josh?
7.
Yep, 7. And my second factor? 3 to the 4th. Okay, we have an expression here. We could do it out. 7 times 3 to the 4th. Let's do it out. So it's 567. Once you've combined that together, there is no way to split that apart again. It's kind of like if I told you I combined two numbers that I multiplied to get 40. You have no way of knowing how I did that. Did I do 2 times 10? Did I do, or I'm sorry,
Because there's multiple possibilities.
4 times 10? Yeah, you don't know. So once you combine it, you can't split it again. Unless I told you 7 was a factor, then you could divide through by it and figure it out. Okay, first thing I would do on this one is, we've got an expression here, we should simplify it. Okay, put your 2/3 back as the exponent. And we just did this out. Okay, 3 to the 4th power. That's 81. You know what, let me change, just so we get a different answer. I don't want to get 0. So 3 to the 4th is 81. What's 81 minus 71?
Or
10, yeah. We talked about 0. You run into a problem if you have 0, so that's why I had to change it.
Are you going to ask us anything when we get 0 on the test?
No, because you'd get an error.
Okay.
All right, so we just did out the arithmetic, make that a little simpler. And now on your calculator, you can do 8 to the 2/3, but all this means is take 8 and square it, and then cube root it. So 8 squared is 64, and then the cube root of 64 is 4. If you're not sure how to do it, that's okay. You just do it on your calculator. And when I recombine these into a single log, would it be a product or division? Yeah.
Division?
Yep, division. 4/10 or 2/5. Natural log of 2/5.
So if you were going to write it out longhand, it would be log base E of 2/5.
Yeah, that's log base E of 2/5. Okay, and I think that's enough. There's some other kinds you can combine, but we'll talk about more tomorrow. Okay, so on 292, I want you to try 1 to 7, 13 to 17, 21 to 27, and 29 to 32. You should not need a graphing calculator for any of the homework tonight. Okay, and tomorrow we have our test on sections 4.3, 4.4, 5.1, and what we did today, 5.4.